We are now going to have a lecture on more related to material balances of reactive systems. And in this lecture, we're going to learn about molecular species balances. So we are going to be doing something very similar to what we did with atomic balances, but this is a different type of balance. And some of you asked me last class why we couldn't, when we had a reaction, why can't we do a balance on CO going in is equal to is related to the CO coming out. And the only way you can do that is with a molecular species balance. So when we did atomic balances, because atoms do not appear or disappear, they are not consumed or produced in a reaction. We can simply do input minus output is equal to accumulation when we have an unsteady state process. And for our steady state processes, we had input is equal to output. So for molecular balances, as we'll see, we have to take into consideration that molecules can be generated in the chemical reaction or consumed in the chemical reaction. And therefore, our balances must include these terms. And for our steady state case, where we do not have accumulation, we still have input plus generation is equal to output plus consumption. So this means that we have to add a degree of freedom for every chemical reaction. And that means our degree of freedom analysis for molecular balances is different than for atomic balances. So let's do an example calculation. Here's a problem that we've already seen. Propane is burned with air. If 1 mole per second of propane is burned with 40 moles per second of air, write the atomic balances. Let's not write atomic balances. Let's write molecular balances. And this time we will see how we do molecular balances. Okay, so we have the additional information that there is no propane in the exhaust and all carbon goes to CO2. So we again balance our chemical reaction. We don't have any CO or any propane in the products, so we can write out the components as mole fractions. We don't need to include propane here because it's all consumed, and we have no carbon monoxide because all the carbon goes to CO2. So we know that all the mole fractions add to 1, and our total outflow out of gas is n dot. So let's do example of molecular balances. Okay, so again, as we did with atomic balances, you need to write out what balance you're doing. So let's do a CO2 balance. We would write this with the term CO2 generated is equal to CO2 out. Because there is no CO2 in the input stream, and therefore, if there's none in the input, nothing can be consumed. So our remaining terms are CO2 generated is equal to CO2 out. And we would write this as the CO2 generated is going to be 4 moles of CO2 are generated per 1 mole of propane consumed. And we know how much propane is consumed, so we put in 1 mole per second of propane consumed, and that is going to equal N of CO2 out. And that ends up being 4 moles per second. Okay, so now I encourage you to turn off the video and do the other molecular balances. Why don't you start with the nitrogen balance? Try to turn off the video and try to do the nitrogen balance. So to do the nitrogen balance, we are going to have N2 in is equal to N2 out because inert is neither generated nor consumed. So we can say that 40 moles, we have 40 moles of air per second times 0.79 moles of N2 is the input. And the output is N dot N2 times and that's what we're solving for. So that's the only unknown. And our N out of nitrogen is 31.6 moles per second. Now try to do the water balance. In the case of water, we have no water going in like the CO2. So the only terms in our balance are water generated is equal to water out. So we can write there's 5 moles of water generated per mole of C4H10 consumed. And we multiply that by the mole of, this is not propane, it's butane. Sorry about that, is equal to N dot of H2O. So we can solve that away and we get N dot of H2O. So the last one we can do is an oxygen balance. Here we go. We have oxygen going in, we have oxygen consumed, and we have oxygen coming out. So we have 3 terms in our balance. So we are going to have 40 moles of air per second times 0.21 moles of O2 per mole of air. That's our O2 in. And we have O2 consumed is going to be 6.5 moles of oxygen consumed per mole of butane times 1 mole of butane. And our O2 out is N of O2. So this is the O2 consumed in this second term here. And we can solve, and we have our answer for the O2 is 1.9 moles of O2 per second. And if we look at our balance, now let's look at our molecular balances. We're going to look at our degree of freedom analysis because it's different from the atomic. Again, we will write the number of unknown labeled variables. We will subtract the number of independent molecular species balances. We will subtract the number of molecular balances on inerts, but we have to add the number of independent chemical reactions present. And we subtract the number of other equations relating unknown variables. And that's going to equal the degrees of freedom. So if we write our degree of freedom analysis for the problem that we just solved, we have five unknown labeled variables. We have 4 independent molecular species balances. We have 3. How does that work? 5 minus 5, CHO. Oh, molecular species. Sorry. Molecular species, we have O2, CO2, H2O, and propane. So we have 4 molecular species. Okay. Then we have 1 molecular balance on independent inert species. Okay. And then we have to add 1 chemical reaction. And we can also subtract 1 other equation relating unknown variables. The sum of mole fractions is equal to 1. And that's equal to the number of degrees of freedom. Okay, so here is the problem. And I'm not going to make this assigned as a quiz, but you should try to do. This is the same process that was in the previous atomic species balance quiz. But since the answers are the same, you should always get the same answers whether you do atomic species balance or molecular species balance. So why don't you try to solve this problem using molecular species?